All right, in this video, we're going to look at question 5 that says to consider the integral of the product of x minus y and x plus y over the region R, where R is the square with vertices at 0, 0, 1, 1, 2, 0, and 1, negative 1. Our job is to compute the integral by first making the substitution x equals u plus v and y equals u minus v. All right, so let's first figure out what this corresponding region is over here in the UV plane. And like we saw in question 3, part B, so let's say compare to 3B, we have a region in the xy plane, but our transformations presented in the format where x and y are functions of u and v. So what we did here in 3B was we solved for u and v in terms of x and y, and that just made the sketch of this corresponding region a little simpler. So let's go ahead and do that first. And notice that since there's a plus sign here and a minus sign here, if I add x and y, I'm going to get u and u is 2u, but the v's will cancel. So x plus y is 2u. So in other words, u is equal to x plus y over 2. Okay. Now if I subtract, I'll get the u's to cancel, and v minus a negative v is 2v. So that then implies that v is x minus y over 2. Okay, not too bad. So now let's go ahead and see what this transformation does to the boundary of our square. So we'll just take one edge at a time. And so for this edge here in green, we have that x plus y is 0. And since I see x plus y in the numerator of u, that implies that u, being x plus y over 2, is constant 0. Okay, so u is constant 0 along the green edge. We can also say that x, being u plus v, is then what? Well, 0 plus v. So in other words, x and v are just the same thing. And since x varies from 0 to 1 on the green edge, that'll imply that v varies from 0 to 1 as well. Okay, so we have that u is 0 and v varies from 0 to 1. So we're describing this unit length segment along the positive v-axis. Okay, cool. Let's go ahead and do the next edge here. We got x minus y is 2, okay, and I see the quantity x minus y show up in the numerator of v. Okay, so this is going to say that v, which is x minus y over 2, would then just equal 2 over 2, which is constant 1, which is, again, pretty nice. Now, the fact that x is u plus v now says that x is u plus 1, because I know v is constant 1. So put another way, u will equal x minus 1. And since x varies from 1 to 2 on the red edge, that would imply that u would vary from where to where. Well, if x were 1, u would equal 1 minus 1 would be 0. And if x were 2, then u would be 2 minus 1, which would be 1. So here we have that v is constant 1 and u varies from 0 to 1. So that's describing this segment right here. Okay, now I'll leave the other two to you, the purple and the blue edge. But as you probably can suspect, okay, this purple edge is going to give us this segment, and the blue edge is going to give us this segment. Okay, so what are we describing here? We are describing the unit square in the UV plane that's sitting here in the first quadrant, right? Which is very, very simple. Okay, great. So now what do we need to do with regards to the integral? Well, this is going to tell us, right, the bounds for u and v are simply from 0 to 1. Okay, so this greatly simplifies the bounds for the integral, okay, because if we were to integrate this function over this original region, I mean, it's certainly doable, but it would be pretty cumbersome because we'd have to use the equations of all these line segments. We'd have to break up the integral, whether we used vertical or horizontal strips. So it wouldn't be exactly the most pleasant computation to make. Integrating though over this unit square here is pretty clean and nice. Okay. Well, what else do we need? Well, we got the bounds. What about the integrand? Okay, what can I say about, say, x minus y in terms of u and v? Well, I could go ahead and just say, well, take x minus y, but see, we've already done that, right? X minus y was, well, 2v, so that's nice. And what about x plus y? Well, again, we've already done that. It's just 2u. Okay, so then the integrand is going to be 4uv. All right, not bad. What remains? Ah, the dA. The differential area element here, right? This thing, we need to first find the Jacobian of the transformation. All right, and so our transformation here, x is u plus v, and y is u minus v. So our Jacobian then will be the determinant of, and here we want to take the u derivative of x, that'd be 1. Then take the v derivative of x, that's 1 as well. Then take the u derivative of y, that's 1. And then the v derivative of y, that's negative 1. So this determinant would be negative 1 minus 1, that'd be minus 2. Okay, so what does that say again? It says that as I map from the UV plane into the XY plane, the area will be scaled by a factor of 2. And remember, this negative just has to do with this orientation reversal that's going on. And don't worry so much about that. But there's a scale factor of 2 there for area. So for us, what really matters is that dA then, which is the absolute value of our Jacobian, times du dv in this case will be, because I'm taking the absolute value, 2 du dv. Okay, so putting that all together now, coming down here, we can say that the integral will be equal to 0, or sorry, the integral from 0 to 1, and then the integral from 0 to 1. As we set up here, our integrand is 4uv, and then we're going to multiply by our area element, which is 2 du dv. Okay, significantly simpler, right? I mean, we're going to have an 8. Notice here I have a product of just u and just v, so I can even split this up. Okay, so this really did make a substantial improvement over the original integral. Okay, so now what are we looking at? Well, this is a half, and that's a half as well. So it looks like we'll get 8 times a quarter, and that's equal to 2. All right, and so that's going to do it. Thanks so much.